All right, Chapter 4, Section 2, Fire Department Hydraulics. Introduction. Hydraulics is the branch of science which deals with mechanical properties of water, other liquids, which application of these properties in the engineering of the firefighters, especially pump operators, must understand and be able to apply principal hydraulics, which are essential for the firefighting. Inadequate training or lack of experience in fire hydraulics can be extremely costly in lives and material. Properties of water. Water, the most common liquid, is the most effective in the various forms of the firefighting. To know use the most effective, however, one should know the physical properties. For all the particular purposes, water is not compressible. It requires 30,000 pounds per square inch to reduce the volume 1%. If the water has a mineral content or such as salt or is subjected to different temperatures, its characteristics will differ. Water consists of 2 parts hydrogen, 1 part oxygen, and in fact are represented by common chemical H2O. The 1 cubic feet of water weighs 62.6 pounds. There are 231 cubic inches in 1 gallon of water, 178 inch, 1,728 inch cubic inches. 1 cubic foot or of water, 1 cubic foot of water contains 7.48.1 gallons. Um, 1 gallon of water weighs 8.35 pounds. The figures are important and should be remembered. Volume. It is often necessary to determine the volume of the cylindrical rectangular containers in order to know the weights of the capacity of installed or reserved tanks, consequently how long they will be in use. To compute the volume, first find the area of the surface of the square of the rectangle. This is down multiplying the length of the width of the, by A equals LW. The circle of the area, equals length times width. The circle of the area is found by the multiplying the diameter squared by 0.7864. Or area equals diameter squared times 0.7854, multiplying the radius squared by 3.146 of the commonly written or area equals pi radius squared, with where Greek letters of pi means 3.1416. Hydraulics and performed formula is first one noted: the area of the diameter times 0.7854. When going from problems dealing with the area of the rectangles and circles to involving the volume of the cylindrical rectangular tanks, consider the third dimensional, that the height of the represented with the symbol H of the formula of the volume of the rectangular tank. The volume equals length times width times height, meaning the volume is found multiplying the length of the width of the height. For example, how many cubic feet are there in a tank? 5 feet, or by 4 feet, by 10 feet. Substituting the formula 5 times 4 times 10 equals 200 cubic feet. When computing volume, all dimensions must be in the same unit measurable. For example, the diameter of the cylindrical container is given in inches, the height is given in feet, and the height and must be covered in inches. The tank contains 200 cubic feet, and then it becomes a simple problem to find its contents. A gallon. There are 7.481 gallons in 1 cubic foot. 1 cubic foot is so 7.481 gallon. Multiplied by 200 equals 1,496.2 gallons. Number of gallons in 200 cubic feet for problems involving volumes of cylindrical tanks using the volume equal the diameter times 0.7864 times the height. For example, how many cubic feet are contained in the tank of the 12 feet in high and 5 feet in diameter? Volume is equal to diameter squared times 0.784 times the height, which is 5 times 5 times 0.7864 times 12 is 232 feet. To find the number of gallons, multiply 235.62 by 7.481 to get approximately 1,763 gallons. Weight. Firefighters must know how to find the weight of the given quantity of water. For example, the vehicle's capacity of 1,000 pounds actually have 8,350 pounds of extinguishing agent aboard. 1 or more than 4 tons of water. Such knowledge would be necessary in making the decision about detouring and crossing the bridge is limited capacity. B. It is necessary to be able to determine the weight of the charged hose line, especially when only limited numbers of personnel are available to move such a line. The futility of the filing of the 2.5-inch hose with water before trying to move it to the point of the operation is revealed after figuring out the weight of the water in 50 feet. Section. This is done by the formula volume times diameter times 0.784 times the height divided by 231 times 8.35. In which the length of the hose is in inches, the diameter is in the hose is inches, 231 number of cubic inches in a gallon, and 8.35 the weight of the pounds of a gallon. Approximately The volume equals 6.2 plus 7854 times 600 divided by 231 times 8.3 equals approximately 169 pounds plus the weight of the hose, which is 65 pounds per section total, approximately 1.71 pounds. To the pull of the 4 foot, to pull 50 feet of the section of 2.5-inch hose totaling something over 1/4 of a ton of the hose water combined up the ladder becomes a formidable task. These calculations also show 1,000 feet of 2.5 inches hose, which in length often carried of the structural pumpers weighs almost 2 tons when filled. 4.0 pressure. Water pressure is proportionally depth of the water with the hydraulics is stated with the pounds per square inch. A column of water 1 foot high exerts pressure of 0.434 pounds per square inch. Tall columns of water, each of the foot 1 foot high, one top of the other, would exert a 0.868 pounds of per square inch of pressure at the base. In other words, common water square inch of the base area, the 1 foot high weights of 0.434 pounds. Effective pressure is pound in square inch. Any point of the column water is equal to 0.43 multiplied by the height of the column above the point in terms of the feet. That is expressed in pi equals 0.434 times the height. H. Which H is the head of it in feet, and the static pressure, the pressure exerted with the water, and the static the pressure determined readily, so that its head is known as the formula as the static pressure is equal to 0.434 times the head basic pressure, pounds and gravity is per square inch exerted by the head of the water against the pump, lifting it to elevated point of the solution is found by the same as the back pressure is equal to 0.434 times the height. The rate of discharge. The rate of discharge is the quantity of water coming over the opening during the given period of time. It's calculated in gallons per minute when the rate of discharge is computed with the two items considered the diameter of the opening nozzle, the pressure of the flow, and the rate of the discharge is found multiplying the diameter squared by the square root of the present shortened time and the constant of 20.9.7. This is expressed in gallons per minute discharge, 29.7 times the diameter times pressure, the square root of the pressure. For example, the formula table of 4 to 1 diameter is 2 inches and the pressure is 36 inches. Then you'd have 128 point gallons per minute. An open housing but no nozzle for the average of the hydrant outlet is open for the 90% efficient nozzle tip of the terms of water volume and this is volume times diameter times 0.784 times the height, which gives you 234.62 cubic feet. To find the number of gallons, multiply 235.62 by 7.481 is approximately 1,763 gallons. All right, 4.7. Weight. Firefighters must know how to find the weight of the given quantity of the wire. For example, the vehicle with the capacity of 1,000 gallons actually weigh 8,350 pounds of extinguishing agent, or more than 4 tons of water. Such knowledge would be necessary to making the decision about detouring the crossing of the bridge of limited capacity. It is necessary to be able to determine the weight of the charge hose, and especially with only the limited number of the personnel available to move such a line with the futility of the filling of 2.5 inches hose of the water before trying to move it to the point of operation is revealed after figuring the weight of the water in 50-foot sections. This is done by means of the formula: volume times diameter times 0.7854 times the height divided by 231 times 835, in which the height of the length of those in the inches of the diameter in the hose of the inches of the 231 and the number of the cubic inches in gallon, number of the cubics, and 8.35 the weight of the pounds of a gallon. Volume is 6.2 times 7.854 times 600 divided by 231 times 8.35 equals approximately 106 pounds plus the weight of the hose, which means 65 pounds per section, totally approximately 171 pounds. To pull the 50-foot section of 2.5-inch hose, totally something over the 1/4 of the ton hose, water combined with the latter becomes the formidable task. These calculations also show that 1,000 feet of the 2,002-inch and a 2.5-inch hose, which in length are often carried by structural pumpers, weighs about 2 tons and when filled. 4.8 pressure. Water pressure is proportional in depth of the water with which hydraulics is stated in pounds and per square inch, and a column of water is 1 foot high, exerts a pressure of 0.434 pounds. I think we read this already. So 4.9 rate of discharge. Rate of discharge is the quantity of the water coming out of the opening during the given period of the time. Is calculated with the gallons per minute. What the rate of the discharge computed with the two items considered with the diameter, opening of the nozzle, the pressure of the flow. The rate of the discharge is found multiplying the diameter squared by the square root of the pressure and system in constants at 29.7. That is expressed in gallons per discharge at 29.7 times diameter times the square root of pi. For example, using the formula table before, one of the diameter 2 inches of the 5.0, the pressure is 36 psi then, and 728.8 gallons a minute. Open hose bolt, and the average of the hydrant outlet is only 9% of the efficient nozzle tip in the terms of water. I just want to see if this is the same as the other page. Rate of discharge, yeah, it was a copycat page. Square roots of 100, number 1 to 100, so for calculating on button the hydrant discharge of the gallons per minute, the formula applied with the nozzle discharge must be multiplied by 0.9. The discharge is 29.7 square root times O2 of the p square rooted times the 09. Apply the hydrant above the example the 713 gallons per minute times 0.9, 64.52 gallons per minute for the all practical purposes, 712.8 and 641.52 would be rounded off to 713 or 642. Drafting. When fire hydrants are not available to supply the water with the firefighting purposes, it is possible to obtain water drafting from the semi-static sources such as the pond or lake river. This is done by dropping one end of the hard suction hose into the bottom of the water, connecting it to the other end and intake of the side of the pump. The pump is started with a partial vacuum and is created with the hard suction hose of the primer. The positive displacement pumps are used and no primer is needed. Atmospheric pressure exerted on the body of the water forces the water through the hard suction hose to the pump. The pump discharges the water until the pressure through the discharge outlet. Atmospheric pressure at sea level is 14.7 pounds per square inch. Water creates gravity of head pressure of about 0.43 pounds per square inch. 1 pound per square inch has a head of 1 divided by 0.434. Therefore, or 2.304 feet. Therefore, the atmospheric pressure of 14.7 can be raised to the water height of 14.7 times 2.304 or 33.9 feet at sea level. However, it must be understood that the figure is theoretical and can be only true when the perfect vacuum can be created. Fire pumps, regardless of the conditions, cannot create a perfect vacuum. A fire pump in good condition should be able to rise water about 75% theoretical height, about 25 feet at sea level. Atmospheric pressure decrease and altitude increase with a rate about 0.5 psi per 1,000 feet. At 5,000 feet altitude, the atmospheric pressure is about 12.2 psi through the water can be raised to 21 feet at this altitude. When pumping the drafting, be careful to ensure that all the gaskets are in good condition, seated with the properly placed. All connections must be tight. An adequate screen should be connected with a hard suction hose to prevent debris into the water from being pulled into the pump. 411. Application of water. Water is the most practical extinguishing aid for ordinary structural fires. It absorbs them rapidly with the greatly capacity of more agents of the fire extinguishment. A great amount of the heat is required to raise the cold water to the boiling point. Much of the more the heat is required to change the water to steam. However, only a small fraction of the theoretical maximum cooling effect is used and the water is applied in the solid stream. To be effective, the water must be reached the base of the fire with the stream spray directed with the smoke does not little more than close the cool atmosphere unless it eventually falls upon the burning material. For a large class of A, for the substantial stream is necessary to penetrate the smoke flame and the fuel. The most efficient fire stream is one of the forceful and large enough to do the job efficient with the excessive water damage. Solid fire streams project water other than considerable area extinguish otherwise inaccessible fire. The protection of the fire streams is primarily concerned for the senior man, but there is also a responsible other crew member for the nozzleman to pump the operator. C. Sometimes the fire, even the structural ones, can be extinguished, but most effective efficiently with the spray or the fog stream. When required the greater pressure to be effective, fog stream do not have the range of the straight stream, but the heat absorption is greater. Well, the water damage is usually when the fog is used because much of the liquid is dissipated as the steam, and it's hot, smoky interior. Firefighters are usually more efficient, comfortable with a fog stream in the front of them. An efficient firefighter must be able to determine the extinguishment requirement for the fire and know the means available for meeting those requirements. Extinguishment is usually simple, but the fire reached for the early stage when it can be extinguished with a booster line with a portable extinguisher. If the fire is not discovered in an early stage of the burning, the extinguishment is usually only difficult because the fire stream must be not only produce by the amount of water required for the extinguishment, but also must carry through the space. The point of the use of the volume can often supply with the small stream, but even these streams must have shape and the velocity to carry the efficiency of the base of the fire. If the fire is not covered with control until the entire building is burning, it can be extinguished only by the using large quantities of water, even though the fire stream must be controlled so that the supply of the greatest amount of the water at a safe distance yet the reach of the fire at the point of the burning. The stage of the fire required heavy master streams. The fast burning temporary frame structure, which had the large areas of broken portions found with the military installation, allowed the fire to spread rapidly. The use of the 1.5-inch hose streams. Most installations depend upon sound judgment resulting from the experience of a senior firefighter. 1.5-inch should not be used for the pumpers unless the 2.5-inch hose is available for support. If the doubt of the 1.5-inch line is capable of extinguishment, use the 2.5-inch line. Large streams of monitoring nozzle deluge sets may be used. The equipment and the adequately water supply are available when the magnitude of fire demands it. 412. Friction loss. Friction is resistant to the motion between the two surfaces. The term of the friction loss in the fire department hydraulic means the loss of energy pressure caused by the friction conditions with which the fire protection personally are concerned, consisting of the water rubbing against the inside of the lining of the hose, causing the turbulence of the water, which in turn sets up another friction that water rubbing against water. The rubber lines of the hose appear to be perfectly smooth to the naked eye. Microscopic observation hose lines shows all series of irregularities which increase the size of the water pressure exerted on the interior of the hose. These irregularities impede the speed of the water as it travels through the hose under the pressure, causing the friction loss, which in turn decreases the amount of the flow of the pressure in the nozzle. The friction loss is always less than the amount of the pressure available at the source when the pump or the hydrant. When dealing with the friction loss of the hydraulics, the loss of the pressure must be exerted follows the water pressure at source with the minus pressure loss of the way equals the pressure as equals the nozzle pressure required for the beginning of the engineering the pressure loss with the way of the friction loss of the pressure which left the nozzle pressure, and the conclusion of the engine pressure minus friction as loss equals the nozzle pressure. Nozzle pressure times engine pressure times friction engine pressure minus friction loss. To put together the nozzle pressure plus the friction loss equals the engine pressure times the nozzle pressure plus the friction loss. These formulas are strictly rule of thumb. They are not technically formulas. 1413. Ideal requirements. Now, the nozzle pressure necessary to be a good fire extinguisher stream. Determine a good stream. The structural firefighting in one way has to be enough pressure to reach for the fire in the solid mass. This means that they must have ample range and they must not break the large fog particles. What drops before reaching the desired range, the ideal structure of the fire extinguisher stream must be capable of discharging 9/10 of the volume of the 15-inch circle of the distance, 50 to 100 feet, depending upon the size and extent of the fire. Experiments has revealed that 46 to 60 pounds the nozzle pressure will do this. This means the average nozzle pressure will be then 40-50 pounds square inches. This is accepted pressure. Since the desired nozzle is known to be the amount of the friction loss in any given hose, laying out the computed added with the 50 pounds of nozzle pressure, the sum of these two figures would be equal to the desired engine pressure. The friction loss varies in proportion to the square of the degree increase of the flow of the water. This when the flow of the water through the hose is double the friction loss increase to 4 times. For example, the 200 gallons of water per minute are flowing through the hose of the friction with a loss of 20 pounds increasing to 400 gallons per minute would bring the friction loss to 80 pounds. 4.14 factors affecting friction loss. Friction loss is verified directly from the length of the line. This means the total friction loss will vary from each of the hose layout. For example, if there's a 10 pounds of friction loss at the 100 feet, or if a 2.5-inch hose using a 1-inch nozzle, there would be 20 pounds of friction loss at 200 feet of the same hose using the same nozzle. Friction loss increasing very rapidly, decreasing in size in the hose if the diameter if the hose with the friction less than 1/32 of it as much as the smaller line, the diameter is halved, and the loss of 32 inches the greater than larger. The friction is 1/2 inch of the hose. The 13 and a half is greater than 2.5 inches hose. Other conditions remaining in the size. Semi-easing. When two hoses run parallel, the single hose with one of the nozzle is attached. They are said to be Siamese. Frequently done prevented with exposure, therefore being increased the nozzle of the friction loss of the 2.5 inches of the lines, same length of 28% is greater than a single line, 2.5 inches of the 26% may be used for the rapid calculation. For example, if there are 10 pounds for the friction loss of 100 feet, the hose there would be 13.5 times their 135 pounds lost, the same length of both 1.5 hose, the other conditions remaining in the same two lengths of 2.5 hose, Siamese and parallel lines would be equal to 1/4 of the tenth of 2.5 pounds. Lost discharge of the same amount of water that shows the volume of the Siamese connection, especially in the use of the heavy streams when large quantity of the water is needed to greater exposure, greater pressure. 416. Effective nozzle and size pressure. For ordinary structural fires have not advanced to the point of becoming exterior conflagration of the one nozzle is due to keep the water damaged, and a minimum will have an ample volume of the pressure extinguish the fire quickly and efficiently. 1 1/4 inch tip that will be discharged 1.5 times as much water as in a 1 inch tip. The 2 inch tip will discharge 4 times as much water in a 1 inch tip. The same nozzle pressure of the large tips are used for the large advanced fires when required greater range and volume. 1 inch tip of 50 pounds of the nozzle pressure will discharge slightly more than 200 gallons per minute with about 10 pounds. And friction loss for every 100 feet for the 2.5 inches hose, so there will be a low pound pressure for the loss of 100 feet of the hose in addition with the friction loss desired nozzle pressure given the engine pressure necessary to supply the nozzle pressure. For example, the 1,000-foot hose out of the 2.5 inch hose using a 1 inch nozzle desiring 50 pounds of the nozzle pressure needed for the engine pressure is determined. See that there is a 10-foot of 100-foot sections in a 100,000 feet flowed. 10 pounds of the pressure loss per 100 feet for the hose is multiplying 10 sections by 10 pounds to get the pounds of friction added to the 50 pounds of the nozzle's pressure required. This example is 150 pounds of engine pressure. D. If the nozzle size is increased to 1/8 of an inch, maintaining 50 pounds of the nozzle pressure flow with the water increasing to 265 gallons per minute. With an 18-pound hose, the friction loss of every 100 feet of the 2.5 inch hose, the nozzle's diameter increased with 1/4 inch for the flow, increase to 325 gallons per minute. The friction loss increased to 25 pounds for every 100 feet, 2.5 inches of hose. Our friction loss of the 5 common nozzle sizes are 50 pounds of the pressure for the calculated with the table 4.2. The ever pump operated with the memorizing of this table so you can tell one tile the engine pressure is required for every type of layout using the 2.5 inch hose. F. When you hose is laid at advanced level above the discharge outlet, pump of the water with the hose exert pressure against the pump. Table 4.2 shows the friction loss nozzle, the 50 pound of pressure with the 3/4 inches of 4 friction pounds per 100 feet of 2.5 inch hose. 7/8 is 8 pounds of friction loss. 1 is 10 pounds a foot. 1 1/8 is 18 pounds. 1 1/4 is 25 pounds. Known as the back pressure. The back pressure is determined in multiplying by the height above the pump, the discharge outlet in feet by the 0.434, the pressure in pounds per square foot, and square inches graded with the 1 foot water. Each story of the building considered with the 12 feet. So the back pressure of each story would be 12 times 0.43 or 5.208 pounds. Or approximately 5 psi, as ample with the hose advanced with the third story, which is 2 stories above the first of the 2 and times equals 10 psi must be added with the pump pressure to compensate for the back pressure of the nozzle size. This should be used to determine the total length of the hose layout and short layout of up to 600 feet with about a 1 inch tip that may be used. The medium layout of 690 feet and is a 1/8 of an inch tip used on a long layout of 900 feet over that ordinarily requires the use of the 1 inch tip. The tip size lower ever might change the discretion of the senior at firefighter. To illustrate the preceding point setup of the situation involving 700 feet of the hose, the medium layout calling for the use of 1/8 of an inch nozzle for the table 4.2, knowing the friction loss factor of the hose is 18 pounds per 100 feet. 7 multiplied by 18 equals 126 pounds of friction loss. This is added to the 50 pounds of nozzle pressure required. The result of the required engine pressure for the 176 pounds. The hose is taken up fourth to the fourth floor. The 3 floors above the first multiplied at 3 times 5 to get the 15 pounds of the back pressure, then add 15 to 176 to get the 191 pounds total engine pressure required for all practicable purposes. The answer is 191 would round it off to 190 nearest the figure divided by 5. One of the most important factors to determine successful failure combating structural fire and effectiveness of the fire stream. The weak stream generally will not achieve the objective. Too much of the pressure will cause the stream to break up and lost effectiveness, and has been determined that 50 psi nozzle pressure will in most cases result in good effective stream. In this, if the chief of the crew in the chart to decide the less of the more pressure is needed, but he will ordinarily single the pump operator to decrease and increase the pressure, but the pump operator should, however, set the initial nozzle pressure at 50 psi. The pump operator, the structural pumper, must be able thoroughly familiar with the equipment on the truck, and they must know how many of the length of the hose of each of the layer in the hose. When the hose has been laid from the truck, the operator should be able to determine how much of the hose was used and laid, glancing at the hose remaining in the hose bed of only the approximately estimate necessary. That pump operator can lays the nozzle of the tip remaining of the truck, determine the size of the nozzle tip is to be used. Knowing the amount of the hose laid inside the nozzle tip, the pump operator determines that the pressure may be maintained at the pump of the producing 50 psi, but the nozzle referring to the pump operator's guide plate. Most structural pumpers employed by the Army are equipped with the pump operator's guide plate installed on the left side of the pumper directly over the near the pumper operator's control. The plate in Figure 1 lists the pump pressure required for the maintaining the desired nozzle pressure for the different sizes of nozzle tips, hose lengths, and ism used in merely as a guide for the pump operators. To read this guide plate, the pump operator must understand which is meant in the changeover of the valve, whatever occurs with the pump when the valve is placed when the two positions. He must understand that the only pump equipped with the changeover are multiple stage pumps in the class 53, 530B, and 530C pumper. Table 4.1 shows the pump operator guide plate used by the Army having a single state pump. However, the two-stage pump is planned for the future. The two-stage pump has two set of impellers which operate with a single shaft. When the valve is placed in parallel volume position, is water entering the pump at the intake side and delivered into both sets of the impeller with simultaneously the impeller force water out of the inch of the impeller, hosing the two massive water joins together with the emerging from the discharge outlet. The valve is placed in the series of pressure position. The water entering the intake of delivered into one impeller, the force of the water throughout the outlet orifice to the other impeller with the turning force that it's out into the increased pressure for the discharge outlet. A heavy zigzag line running down across the guide plate shows the pressure required. This line divides the charter in half, and so the non-contributory operating single-stage pump. However, the operating two-stage pump with the changeover of the valve with the pumping of the pressure listed and left over the heavy line to be sure that the changeover of the valve with the power will position the pump with the pressure listed to the right of the heavy line. See that the changeover of the valve is in the pressure of the series position. Note that the pressure given in the chart are actual pressure. The pressure gauges are various pumps and will vary in calibration that may be calculated in 2, 5, 10, and 50 psi. The possible LC is setting up the pump or the pressure that nearest to the calibration of the gauge on that specific truck. Section 3. Hose ladders and pumper drills.